Hi, my name is Shahnawaz. In this lecture, we are going to study the radicals. The radical of an ideal. So we'll start with the definition of a radical of an ideal. So we have this definition. So let I be an ideal in a ring A. So A is over a ring which is commutative with identity element. So then the radical of A, radical of I denoted by R of I is defined as this R of I consists of all those elements in ring A such that there is some positive integer n such that the nth power of A is an element of I for some integer n greater than 0. So this n has to be a positive integer. So then this R of I is called the radical of ideal I, and we claim that this set is actually an ideal of ring A. So this is, let us make this a proposition. So R of I is an ideal of A for any ideal in A. Ideal I in A. So there is a standard way to prove this. So let us prove this. So let I be any ideal in a ring A. And let pi from A to A mod I be the canonical projection. That means this pi takes an element in A, so it is coset by I. So A goes to A plus I. So then we know that the inverse image of any ideal of A mod I is an ideal of A. So let eta of A mod I be the nil radical of A. Which means n sub A mod I consists of all nilpotent elements in A mod I. So then pi inverse of eta of A mod I is an ideal of A, since this pi is a ring homomorphism, and a ring homomorphism pulls back ideals into ideals. So where this pi inverse of net of A mod I is actually all those elements in ring A whose image belongs to the nil radical of A mod I, which is same as to say that this set consists of all those elements of A such that this pi of x is same as x plus I is in the nil radical of A mod I. Now by definition of the nil radical of A mod I is that this element is nilpotent there, i.e. there is some positive integer n such that x to the power x plus I to the power n is the identity zero element of A mod I, which is actually I. That is what we mean by a nilpotent element in A mod I. This is same as all those elements in A such that x power n plus I is same as I, or this is a set of all those elements in A such that x power n is in I, and this is the definition of actually the radical of I. So let us write this down here. So this is for some n greater than 0. This is again true for some n positive, for some n positive. So this is actually the radical of I by definition. So that means this radical is actually the ideal of A. So this is one way to prove it. The other way is a formal way, i.e. we have to prove the radical is closed under addition and the external multiplication. So alternatively, so now let us prove the other way. I mean, to prove radical is an ideal of A, we are going to prove it is closed in both operations. So let x and y be two elements in the radical of I. So then that means there exists some positive integer, say r and s, such that x to the power r and y to the power s are both the elements of I. Now let us consider, so now consider the element. So let us consider this element here, x plus y to the power r plus s. So using binomial theorem, this is actually, say I goes from 0 to r plus s choose I, x to the power I, r y to the power r plus s minus I. So if we investigate the terms in this expression, so what we observe here, so suppose if this I is bigger or equal to r, then this term is going to be an element of I, because x to the power r is element of I. So x to the power any element which is bigger than r is also an element of I. Hence this is the element of I. So let us write this down. So now if I is bigger or equal to r, then x to the power I, and hence x to the power I, y to the power r plus s minus I is an element of radical of I. The element of I. So this is the element of I, and hence now suppose this I is strictly less than R. So this is the other way. Now if I is less than R, then this sum over here, so then R plus S minus I is bigger or equal than, now since I is bigger than I is less than R, so this is same as R plus S minus R, so this is equal to actually S. So this means this sum over here, this is bigger than S here. So then y to the power R plus S minus I is an element of I, and hence x to the power I, y to the power R plus S minus I also belongs to I. So this proves that each term in this sum is actually an element of I. So this further implies, so this implies that x plus y to the power R plus S belongs to I, or equivalently x plus y is in the radical of I, or equivalently x plus y sits in the radical of I. So this proves that this radical of I is closed under addition. Now let us prove it is closed under multiplication as well. So let A belongs to A and x belongs to rad of I. Then there exists some n positive such that x to the power n is in I. So this implies if I look at this element a to the power n, x to the power n, which is same as ax to the power n. Now a being an element of A and x being the element of I, this means ax is also an element of ax to the power n is also element of I, because x to the power n is an element of I. So this belongs to I, and hence this means ax is in the radical of I. So this proves that I is rad of I is ideal of I. Now let us do some properties of these radicals. So we have the following exercises. So we have the first item which says so let us first write, let I j be ideals in a ring A, then the first item is I contained in J implies radical of I is contained in radical of J. This is the first exercise. The second is that I is always contained in the radical of I, i.e. the radical of I is a bigger ideal than I. And then we have the third item, radical of the product ij is same as radical of the intersection, which is same as the intersection of radicals. And then we have the fourth item. A radical of sum is actually a radical of sum of radicals. And finally, then we have a radical of ideal I is the unital ideal if and only if I is unital. And finally, radical of so if P is any prime ideal, then for any n greater than 0, radical of p to the power n is actually p. Now let us prove these exercises. So first we have to prove if a is contained in b, then radical of a is if I is contained in j, then the radical of I is contained in radical of j. So let x belongs to a radical of I, then x to the power n is in I, where I is contained in j for some n positive. Now since this x to the power n is element of j, this means x is in the radical of I. So therefore x is in the radical of j, but this x was chosen from the radical of I, and that means hence a radical of I is contained in radical of j. Now we have the second item. So we have to prove I is always contained in the radical of I. So let x belongs to I. So this implies x to the power 1 is in I. Now if some power of x is in I, that means that element is in the radical, or x belongs to the radical of I. Hence this I is contained in the radical of I. Now let us prove the third item. So we have to prove radical of the product is the radical of intersection is the intersection of radicals. So now let us prove this. So now since the product of ideals, so since I dot j is contained in the intersection ij, we have radical of ij is contained in radical of I intersection j. So this follows from item first. Now let x belongs to the radical of I intersection j, then x to the power n belongs to I intersection j for some n positive. So this implies now x to the power n belongs to I intersection j means x to the power n is in I as well as in j, i.e. x is in radical of I as well as in radical of j. So this implies x belongs to radical of I and radical of j, and hence in their intersection, and hence x is an element of their intersection because it lies in both radical of I as well as radical of j. So this proves that this x was chosen here. So this proves that, so this shows that radical of I intersection j is actually contained in radical of I intersection radical of j. So this proves this containment here. Now finally that so now let x be an element of radical of I intersection radical of j, then there exists m and n positive such that x to the power n is in I and x to the power m is in j. Now x to the power n being an element of I and this being an element of j means, so this shows that, so if I look at the product x to the power n plus m, which is actually x to the power n times x to the power m. Now this being an element of I and this being an element of j, so this is in the product. That means this is in the product of ij, so which further implies x is an element of radical of ij because some power of x is in ij, so this implies x is in the product of radical. So this x was chosen here and this x ended up here, so this means, so this implies radical of I intersection radical of j is contained in radical of ij. Now let us see what we got. So first of all we see here this containment, so hence radical of ij is actually contained in radical of I intersection j. So this is from here. Then we see here this intersection radical of I intersection j is contained in radical of I intersection radical of j. So this is contained in radical of I intersection radical of j. So this is further contained in, because radical of I intersection radical of j is contained in radical of ij. So this is contained in radical of ij. So we started with this thing over here and we ended up at the same thing. So this proves that a radical of ij is actually a radical of I intersection j, which is actually radical of I intersection radical of j. So this is what we got here. Now let us prove the next item. Now by the given exercise. So fourth item is radical of I is the unital if and only if I is unital ideal. So let us prove this. So this is very trivial. So I think this is actually unit item fourth. So let x belongs to the radical of I which is by definition the unital ideal. This means x this means this 1 is in the radical of I, so this implies 1 is in the radical of I, and hence 1 is in the I. So this further implies I is the unital ideal because 1 is unit, so the ideal generated by 1 is actually the unital ideal. So this means I is the unital ideal. So now suppose I is a unital ideal, so suppose I is unital, then this unital ideal, which is called I, is contained in the radical of I by item second, and radical of I is an ideal in A, and A is actually the unital ideal. So this means that the radical of I is actually the unital ideal, because so this implies a radical of I is a unital ideal. So this proves this item. Now let us prove the next item, that radical of sum of two ideals is radical of sum of radicals. So this is easy to prove. So since I is contained in radical of I and J is contained in radical of J, then I plus J is contained in radical of I plus radical of J. So this is trivial, and by item first, that the radical respect is the inclusion. That means if I is contained in J, then radical of I is contained in radical of J implies, so this would imply, this implies radical of I plus J is actually contained in radical of I plus radical of J. So this containment is trivial. Now to prove otherwise, so conversely, let X be an element of radical of I plus radical of J. That means then there exists some n positive integer such that x power n is an element of this ideal radical of I plus radical of J. Now if this is the case, that means there is some element in radical of I and some element of radical in J such that x to the power n is sum of those two elements. So then there exists A in radical of I and B in radical of J such that this element over here is sum of these two elements. Now A being an element of this and B being an element of this implies, so equivalently there exists say R and S positive integers such that A to the power R is element of I and B to the power S is element of J. So now if we investigate, so if we look at this term x to the power n times r plus s plus 1, which is actually equal to x to the power n times r plus s plus 1. So this must belong to the radical of a plus b, sorry, radical of I plus j. So because x to the power n is actually a plus b, so x to the power n power r plus s plus 1 is actually a plus b to the power s r plus s plus 1. So by investigating the terms, in the binomial expression of x to the power n power r plus s plus 1, we have this thing. So this proves radical of sum of two ideals is actually radical of I plus radical of j. So hence this proves this item. So finally we have the last item, that is the sixth item. So we have to prove if p is a, so let p be a prime ideal and n belongs to z be a positive integer. That means then, so we have to prove radical of p to the power n is actually p. So then this p is actually contained in p to the power n, and this p to the power n is contained in the radical of p to the power n. So this containment is trivial. P is contained in the radical of p, so that is p is contained in radical of p to the power n. Now to prove converse, so now let x belongs to the radical of p to the power n. So then there exists say k positive such that x to the power k is in p to the power n. Now p being a prime ideal, so this would imply, so this implies that either x belongs to p or x to the power k minus 1 belongs to p. So since this is true for any power, so this means, so this would imply, x is an element of p, because if x to the power k minus 1 is in p, so this would imply x times x power k minus 2 is in p. So that means p being a prime, either this is there or this is there. If this is there, we are done. Now if x to the power k minus 2 is there, doing the same procedure, we will get x is the element of p. So thus radical of p to the power n is p. So this proves the last item.